All right, Chapter 7, Think and Discuss. So consider two identical balls released from rest on tracks A and B shown when they reach the right ends of the track, which will have a greater speed. The speeds will be the same, assuming that the curve is basically the same at the very beginning in terms of the drop. They both start with a certain amount of potential energy. They both lose potential energy and gain kinetic. In B, it loses a little bit more, and then it loses a little bit more potential energy. In other words, it gets faster on that segment down there, and then it gains potential energy, loses kinetic energy, loses speed at the very end. But the amount it gains when it goes down the second ramp is equal to the amount it loses when it goes up the first ramp. So they'll have the same speed at the end. However, the one that at the very end of it, recognize that in B, it will get to the end of the track faster, or sooner, I should say. It takes less time to get to the end of the track at B because there is that segment where it is traveling faster in B than it is in A. And then it asks you to compare, think, and discuss 795 on Chapter 3. I assume it's asking the same question. It's harder to justify it in Chapter 3 because we haven't really... Energy is a much easier way of looking at it than, the force acting on it gives it a certain acceleration, and then it has the negative of that acceleration going the other direction. It's more of a conceptual than energy is just easier there. 103. The sun puts out twice as much solar energy in 2 hours than it does in 1 hour, but the solar power of the sun is the same from 1 hour to the next. Distinguish between solar energy and solar power. Power is, again, energy used per time, and so if it's twice as much time, it's twice as much energy, but if it's producing the same amount of power each time. So, for example, if I do 5 watts of work, that means I'm doing 5 joules every second. So in 2 seconds, I do 10 joules of work. 3 seconds, I do 15 joules of work. It's this. So the amount of energy I'm using or putting into a system gets bigger the longer I'm going. However, the power is still the same. The similar analogy would be if I'm traveling at 5 miles per hour, every hour I go an additional 5 miles. So my speed is the same the entire time, but the distance I travel increases the longer the time interval. 104, golf ball and ping pong ball both move with the same kinetic energy, which has greater speed. Again, 1/2 mv squared. We assume a normal ping pong ball and a normal golf ball. Golf balls have more mass than a ping pong ball. And so therefore, since 1/2 mv squared is the formula we're working with, the more mass you have, the less speed there is. So a ping pong ball with the same kinetic energy would have greater speed. Then it goes on, similarly, in a gaseous mixture of heavy molecules and light molecules with the same kinetic energy, which has the greater speed, well, the light molecules have a greater speed. In 109, your discussion partner is confused about the ideas discussed in Chapter 4 that seem to contradict ideas in this chapter. For example, in Chapter 4, we learned that a net force is 0 for a car traveling along a level road at a constant velocity, but in this chapter, we learned that work is done in such a case. Your discussion friend says, how can work be done when the net force equals 0? Yep, that's the new dog right there. Recognize that work is being done try it this way. So if I'm driving along at a constant velocity, in reality, I've got friction involved there. It is not 100% efficient. I can't go into, let's just say, a flat state like Nebraska, put it on 50 miles per hour, take my foot off the gas pedal without cruise and just let it go. There is heat being generated. There is friction between the bearings. It's not 100% perfect. Something's being lost, so I have to have my foot on the gas pedal. Now, not a whole lot, but I need some in order to be able to put more energy back in the system. So work is being done in order to offset the amount of work that's being done against it. So, for instance, in a problem earlier, if I'm pushing on a crate with 100 newtons of force and the velocity is constant, that means there's 100 newtons of force of friction acting against it. So if I've got 100 newtons this way and 100 newtons that way, both are doing work. One's doing positive work, one's doing negative work, and so the total work is 0. 114, when the driver applies the brakes to keep a car going downhill at a constant speed and constant kinetic energy, tuned out as I was reading it. When a driver applies the brakes to keep a car going downhill at a constant speed and constant kinetic energy. So Constant kinetic energy, that means the mass times speed squared is constant. So since he already said constant speed, the constant kinetic energy is just stating that the mass of the vehicle is staying the same. The potential energy of the car decreases. Where does this energy go? This is primarily heat. If your brakes need some work, you might hear the squealing sound, but things are getting hotter down there. In contrast, where does most of it go in a hybrid vehicle? Again, it should be going in. It should be going into heat as well there. 117. No work is done by gravity on a bowling ball that is. Oh, actually, in a hybrid vehicle, no, you're applying brakes. I don't think that changes just because you're in an electric vehicle. 117. No work is done by gravity on a bowling ball that is resting or moving on a bowling alley because the force of gravity on the ball acts perpendicular to the surface, similar to the normal force, also acting perpendicular to the surface. But on the incline, the vector component there is a vector component parallel to the alley, as in B. How does this component account for the acceleration of the ball and the work done on the ball to change its kinetic energy? So when the ball is moving horizontally on the level floor, the kinetic energy basically it's going roughly the same speed. There's no work being done. Now the ball is turning. There's friction between the ball and the lane. That friction is there, but it's technically, if it's a perfect roll, that's static friction. When you first throw it, though, sometimes it'll slide a little bit before it starts to roll. In that case, there's kinetic friction involved, and so it is slowing down in that case. But once it gets into the ideal roll, then the friction is static, and therefore there's no loss from that, because technically what's happening on the ball is a point touches down and then picks up again, touches down and picks up. And so the friction's acting this way, whereas the contact is perpendicular to that. So acceleration of the ball, if there's no work being done, then there's no change in kinetic energy, therefore there's no change in speed. We assume that if no work is being done, well, actually, that's misleading there. If it's going in a straight line, they did say bowling alley. We'll assume you can't put English on the ball. Then there's no change in speed. If it's a straight line, then there's no change in velocity, so acceleration is 0. Yet downhill, part of the force is down the ramp, and so the part of the force that's down the ramp is equal to the mass times acceleration of the ball. If it's sliding, if it's rolling, there's some torque involved that's more complicated than that. And we'll touch on that a little bit in Chapter 8. But since force is being applied to it, and it is moving in that direction, work is being done. And I think I pretty much hit the essence of 117. 118, consider a bob attached by a string, a simple pendulum that swings to and fro. Why doesn't the tension in the string do work on the pendulum? And that, again, is perpendicular. That the tension is this way as it swings back and forth. It is moving perpendicular to the force, and therefore no work is done. Explain why the force of gravity on the pendulum at nearly every point does work on the pendulum. That is because, say, when it's out like this, you have a force of gravity that's acting downwards. And so as it swings, there is part of that force in the direction of movement. You would break, I guess that way. You would break the force down into components. Part of it is along the line of the tension. Part of it is perpendicular to that. Because there's part of the weight is perpendicular to it, the work is being done. The one place where work is not being done by the force of gravity is at the very bottom, because at that point it's moving this way and the weight is this way. They are perpendicular to each other. And then C, what is the single position where the pendulum, there's no work done by gravity, it's that point. And that is Chapter 7, Think and Discuss.